Let's look at graph sketching. One of the applications of differentiation is how differentiation helps us look at the shape of a graph and in the end to be able to sketch a graph from beginning to end. Now I'm going to do this via examples. These videos are going to be a little bit longer because there's a lot of aspects to look at it. If we want to sketch a graph, there's the next things we'll need to look at. We need to know the domain of the graph. We need to look at the intercepts. We need to look at where the function is increasing and decreasing, relative extrema, intervals where the function is concave up and concave down, inflection points, and asymptotes. Once we have all this information, we can sketch the graph. So I'm going to be looking at 2 examples. I'll do a video on each. They're going to be a little bit longer because I'm going to look at each and every one of these aspects. Now, if you're only interested in one of these aspects, you can scroll through the video till you get to that part, but we're going to do it systematically so that we get to the point of having all the information we need to sketch the graph. So the first function we've got x squared over x squared plus 3. It's a rational function that we want to sketch. So we start with the domain of this function. All the x values that I can substitute in, that won't cause trouble, and we can see the denominator is never going to be 0, so all real numbers is my domain. If I look at my intercepts, when x is equal to 0, y is going to be 0, so 0, 0 is going to be one of my intercepts. And when y is 0, the only option is for x to be 0. So there's only one intercept, and that's 0, 0, the origin. All right, so we've got our intercepts. After our intercepts, we now have to look at where my function is increasing and decreasing and where my relative extrema is. And for that, we use the first derivative. So the first derivative comes in handy for increasing and decreasing and relative extrema. So let's look at what this first derivative is. We're going to have to use the quotient rule. It's the denominator squared, the derivative of the top, the numerator times the denominator, minus the numerator times the derivative of the denominator. So that we can simplify. We'll get 2x cubed minus 2x cubed, 6x in the numerator, and my denominator x squared plus 3, everything squared. Now my derivative, we know our theory tells us when the derivative is positive, my function is increasing. When the derivative is negative, my function is decreasing. And I look at the critical points. That's where my derivative is 0 undefined, to look for extrema. So however you set it up, we want to see what values will make this derivative 0 undefined. It will never be undefined, and x equal to 0 will make it 0. So if x is equal to 0, I'm going to do it in parts. 6x is going to be 0 if x is 0. This is just a number line at the top. For any negative values, 6x is negative, and x squared plus 3 squared is always positive because it's a square of something that can't be 0. So my derivative is going to be negative, 0, and negative. So interestingly enough, I've made a mistake. Our only critical point is going to be 0. This is a number line. That's 0. My numerator will be 0. My denominator will never be 0. The denominator is always going to be positive, so it's not even going to influence the sign of the derivative. If x is equal to 0, my derivative is going to be 0. If x is negative, my derivative is going to be negative, and x is positive, my derivative is going to be positive. So this function is decreasing over there and increasing over there. So y is decreasing on the interval minus infinity 0. Y is increasing on the interval 0 to infinity. Now we're going to look for relative extrema. The only place to look is here at 0. Is my original function defined at 0? Yes, the original function is defined at 0. My function goes from decreasing to increasing. So here at 0, y has a local minimum at the point 0, and y is also 0 there. Substitute the 0 back into the original function. Whether you use the word local minimum or relative, it means the same thing. All right, so that's the first bunch of information I get from my derivative. Now my second derivative talks about concavity of the graph. The second derivative we need to find, we're going to have to use the quotient rule again. It's x squared plus 3, everything squared. 6 times x squared, so it's to the power 4. 6 times x squared plus 3 squared minus the derivative of the denominator, which is 2 times x squared plus 3 times 2x times the numerator, which is 6x. Now you can go simplify it. It's going to take a bit of time. I'm going to leave that with you. Just pause here, try and simplify it, and you should get the following. Minus 18 x squared minus 1 over x squared plus 3 cubed. All right. Now what critical values do I have there? What will make my numerator 0? That'll be plus or minus 1. And yet again, my denominator won't always be, it'll always be positive. I've got an x squared plus 3 to the power 3 is always positive, so I'm not worried about that. Minus 18 is always going to be negative, so let's not forget about the minus 18. That's always negative. X squared minus 1 is 0 at minus 1 and at 1. For values between minus 1 and 0, minus 1 and 1, I will have a negative, and it's going to be positive everywhere else. So then bring it all together, and my second derivative is negative 0, positive 0, negative. So negative second derivative means concave down. So y is concave down on the interval minus infinity to minus 1, and then again from 1 to infinity. Y is concave up on the interval minus 1 to 1. So inflection points is where concavity changes, given that my original function is defined at that point. So minus 1 and 1, concavity changes from a negative to a positive, from positive to a negative at both those values. My original function is defined at minus 1 and 1. So y has inflection points at where x is minus 1, and I need to calculate the y value, and where x is 1, I need to calculate the y value. And I calculate those y values by substituting back into my original equation, and I will get a quarter for both of them. So those are my inflection points. So all we've got left to do before we sketch this graph is to look at the asymptotes. So let's take a look. So to find the asymptotes, firstly, if we look at horizontal asymptotes, we look at the limit as x approaches plus or minus infinity of this function, x squared over x squared plus 3. So you can use any of the techniques we've looked at in limits, either L'Hopital's rule or just use the shortcut, but you will see that tends to 1. So the horizontal asymptote is y equal to 1. Vertical asymptote where is this function undefined? The denominator is never 0, so there's no vertical asymptotes. So now we need to bring together everything we've got to sketch this graph. Now, it's a good place to start with the asymptotes. I know here at y equal to 1, my graph is going to tend to that as x goes to positive or negative to infinity. So at the ends, it's going to go towards 1. So let's look at what else we have. Other points we've got is the intercepts is 0, 0, so the graph must go through this point. It's always easier to put the points on first and then look at everything else. I've got a minimum at this point, so I'm just going to put some dotted lines here so that I've got an idea of what shape my graph goes. That's a minimum. It's decreasing before that, increasing after that, and it's going to the asymptotes. The inflection points I've got is at minus 1 1/4 and 1 1/4. So the inflection points is at minus 1 and 1. So there's an inflection point and there's an inflection point. So now my function is decreasing, and this is a horizontal asymptote. So it has to look like this. Concavity changes here. Concavity changes there, and it's increasing. Now it's concave down all the way to minus 1, and the natural curve actually got me there. Concave up between minus 1 and 1, as our table showed here, and then concave down again after 1. So that's this function sketched from beginning to end. I'm going to do another video with another function that looks a little bit different.